Now we're going to take a look at a dehydration. And dehydration is effectively just losing water from the molecule. When we dehydrate an alcohol, what we do is we lose H and OH across two carbons to form an alkene. So here's a dehydrating agent that's commonly used, phosphorus oxychloride along with pyridine. And we're going to go through the mechanism for this in a second, but let's just first predict the product. So we have our OH, which is right here, and that is on what we would call an alpha carbon. And to do the dehydration, we need a hydrogen on a beta carbon. So we have a beta carbon here and a beta carbon here. Both beta carbons contain hydrogen. So on the left we have one beta hydrogen, on the right we have two. This particular reaction follows Zaitsev's rule. So this is an elimination where you're eliminating H and OH across the bond. And with Zaitsev's rule, the elimination will occur that gives the most substituted alkene. And that's just a stability factor. More substituted alkenes are more stable and they're favored. So if you were to eliminate the OH and hydrogen across this alpha-beta bond, you would just end up with a disubstituted alkene. But if we instead choose the hydrogen over here and eliminate across the alpha-beta bond on the left, let's look at what we get. In this case, we get a trisubstituted alkene. Let's draw the other possible product. This one is just disubstituted. So the product on the left is the actual product. Let's go through the mechanism and see how this dehydration occurs. All right, so again, I want to simplify it just a little bit. I'm going to do RCH2OH so that we have an alpha and beta carbon to work with. So the first thing that happens is this reacts with the phosphorus oxychloride. So I'm going to use the lone pair on the oxygen and draw a curved arrow to the phosphorus and then push a pair of electrons up onto the oxygen. Now we'll draw the intermediate that forms here. We have the oxygen, which still has a proton, and the new bond to the phosphorus. And that will be O-, and we still have the 3 chlorines attached. And don't forget the positive charge on this oxygen. Next, the PO double bond really wants to reform because the double bond is more stable than the single bond. So what we'll do now is use the lone pair on this O-, push that down to reform the double bond, and then lose Cl as a leaving group. So now we have the P double bond O and just 2 chlorines attached. Next, we're going to use the pyridine as a base to get rid of this proton on the O+. I'm just going to abbreviate pyridine as PYR with its lone pair. We'll come up and take this proton off of the oxygen. Draw the byproduct, PYR, H+. And that pyridinium ion will be counterbalanced by the Cl-. All right, so now we have this oxygen with the big phosphorus group on there. What we're going to do is finish this up with the elimination step. So I'm going to use pyridine once more as a base. And we have the 2 beta hydrogen right here. So the pyridine will grab one of those. These electrons will come down to form the double bond, and you'll lose the oxygen as a leaving group. So what we end up with, we have the R and the double bond. Then the byproduct will be P double bond O, O minus, and the 2 chlorines. And of course, the second protonated pyridine. So this is how we end up with our alkene product.